In this video, you're going to learn how to work with permutations, combinations, factorials, as well as how to calculate probabilities. What we're going to do is we're going to go through the concepts first here briefly, and then we're going to dive into 15 word problems, story problems, so we can get some practice, applying these concepts. So let's start off with a basic example. Say, for example, you have the letters H, A, and T spelling the word hat. And say we wanted to find out how many different permutations are there of the letters in the word hat. Now, when you think of the word permutations, permutations refers to like an ordering. So like how many different ways can we order those letters, all three of those letters? Now, let's just go ahead and do it by hand here so we can see H-A-T. We could also write it as H-T-A. We could do A-T-H or A-H-T. Or what else? T-A-H or T-H-A. And those are the only possibilities. So sometimes this is referred to as a sample space, basically showing you like all the possible outcomes. But these are the permutations, the orderings. Another way to do this, you can do a tree diagram. You could say like, imagine if I put these three letters into like a hat. Okay, like this. Here's our three letters on sheets of paper. Let's just say H, A, and T. And what we're doing is we're going to reach into that hat and we're going to pick out a letter. So for the first letter, we could pick an H, an A, or a T, right? But if we pick an H and we set it aside, when we go to pick the next letter, what can we do? Well, we could either pick an A or a T, okay? And then if we pick, let's say, an H and an A, there's only a T left, right? Whereas if we pick an H, a T, then there's only going to be an A left. And same thing over here, we could do A, T, or H, or if we do A, T, then this would be like an H, and this would be like a T, or we could do A or H, and then this could be an H or an A. And so basically, if you kind of think of this as like a route, you could either go down this route, H-A-T, or H-T-A, or A-T-H, and that's another way of getting these permutations or possible permutations. Another option is to use what we call a factorial. See that exclamation point there? That doesn't mean like, yay, right? It means you take the number and you multiply down to 1. So for example, in this case, we had three letters, H, A, and T. So we'd say, well, there's three possibilities for what we can pick out for that first letter. Once we pick out that first letter, there's two choices for the second letter that we pick out. And then lastly, there's only one letter for the final choice. And so this is really 3 times 2 times 1, which is 6. Or you can write this in a more condensed fashion, 3 factorial. And that represents 3 times 2 times 1. So n factorial is when you're trying to see how many different orderings there are of all n items. Now, sometimes what happens is you only want to maybe pick 2 of the items or 1 of the items, okay, or like that. So in that case, you would use this concept here of NPR. What does that mean? It means out of n items, how many ways are there of picking R of those items where the order is important? We're also going to talk about combinations, okay, combinations, and this is when the order is not important. But let's talk about the permutations first. So NPR, let's say for example, out of the 3 letters here, how many ways are there to pick just 2 of the letters where the order is important? Well, let's try to write it out again. So what we could do is we could say, well, there could be H and A, or there could be A and H, or, so that's one possibility. Another possibility, we could do T and H, or we could do H and T, and we could do A and T, or T and A. And so you can see here that there's 6 different possibilities of choosing 2 letters out of 3 where the order is important. Now, we can use this formula. This is another way to do it. You could say n factorial, so that's going to be, so we're doing 3p2 out of 3 items. We're picking 2 where the order is important, so that's going to be 3 factorial over 3 minus 2, which is 1 factorial. Now remember, we already talked about how factorials you multiply down to 1, so this is going to be 3 times 2 times 1, which is 6, all over 1 factorial, which is just 1. So you can see there's 6 different possibilities, and these are the 6 that we just wrote down here. Now, what happens if you're not concerned with the order? That's what a combination is. So if we said how many ways are there to choose 2 letters out of 3 where the order is not important, what we would have is H and A and H, those would be like the same like outcome. It's the same 2 letters. So you'd only count that once. T and H and T, those are the same 2 letters. We'd only count that once. A and T, T and A, we'd only count that once because it's the same 2 letters. So what we could do here, we could say 3C2, okay, 3 combination 2 equals 3 factorial over 3 minus 2, which is 1 factorial, and then times R factorial, which is 2 factorial. Now you might be saying, you know, these formulas look very similar to one another. The only difference is we're dividing by this R factorial. What that R factorial is doing is it's dividing out the multiplicities, meaning that you're not going to count H and A and H as the same, as 2 different ones. You're going to count it as the same outcome, right? So you don't want to double count. And so that's what we're doing, is we're basically saying H and A and H, we don't want to double count that, so we're dividing by 2 factorial. So if we simplify this, we get 3 times 2 times 1. 1 factorial is 1. 2 factorial is 2 times 1. You can see these are canceling, and 3 divided by 1 is equal to 3. And you can see we got 3 outcomes here. So one other thing that's important to remember, when you have this n factorial, 1 factorial we said is 1. 0 factorial, you have to memorize this one, it's also equal to 1. So if you get 0 factorial, just realize that's 1. So let's dive into some of the word problems, and you'll get a better feel for how to work with these permutations, combinations, factorials, and even probability, which we're going to talk about in just a second. Now, when we talk about probability, what probability is, it's the number of successful outcomes, or what you're looking for, what you want, divided by the total possible number of outcomes. And that's why we're talking about permutations and combinations first, because that tells us the number that we're dealing with, the number of successes or the number of total possible outcomes. But when you think of probability, it's written as a fraction or a decimal, unless they say what's the percent chance that something could happen. But basically, probability, again, is just talking about the number of what you want divided by the total, and that's what our permutations are going to give us, our combinations are going to give us, our factorials are going to give us. So let's dive into some word problems. When you're doing these problems on your homework or just trying to solve problems on your own, you may not have problems that are exactly like these problems, these 15 that we're going to do, but you'll have ones that are similar. So if you understand these concepts, you can apply them to additional problems that you're working on. So let's go through this variety of problems. So starting with number 1, it says, how many distinguishable permutations are there of the word mathematics? So basically, again, they're talking about permutations. That's saying how many ways are there of ordering all these letters so that it forms a new quote-unquote word. Well, there's a lot of letters here. If we had to write them out by hand, we would grow old and die, because it's going to take a long time, right? So an easier way of doing this is, let's count how many letters there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 factorial ways, okay? Remember we talked about n factorial? There's 11 factorial ways of ordering all those letters. But you see how there's some repetitions? We have 2 m's, so we're going to divide by 2 factorial. There's 2 a's, so we're going to divide by another 2 factorial, and there's 2 t's, so we're going to divide by another 2 factorial. Now, if there was 3 t's, we divide by 3 factorial. Or if there was 4 r's, let's say, you divide by 4 factorial. And the reason is, like, 2 factorial is 2 times 1, meaning there's 2 different ways to take these m's and, like, interchange them, but it would form the same word, mathematics. You wouldn't even know that anything was different about it. And so that's why it's saying distinguishable, meaning you can tell that they're different. So what we're going to do now is we're going to go to the calculator. You should have a factorial button. If not, you can just do 11 times 10 times 9 all the way down to 1. The factorial is probably under a probability key that you have on your calculator. That's what mine's under. And then I'm going to divide by 2 factorial, which is 2 times 1, 2 times 1, 2 times 1, which is 8. So I'm going to divide 11 factorial by 8, not 8 factorial, but just the number 8. And that's coming out to 4989600. So basically almost 5 million different ways of ordering these letters such that it forms a new quote-unquote word. Okay, quite a few. So number 2 now, let's look at this one. It says, if there are 20 people in a bike race, how many ways are there of awarding a first, second, and third place medal assuming that there are no ties. Okay, a little bit different problem here. So now what we're trying to do is figure out, out of 20 people, we want to know how many ways there are of picking 3 of those people to be the first, second, and third place finisher. And oftentimes what you want to ask yourself is the order important or is it not important? So if I change like person A, B, and C, C, B, and A, does that result in a different outcome? Well, yes, because in that case, they would be getting different medals, gold, silver, bronze, or, it'd be a different order. So in this case, because the order is important, we want to use the permutations, and we're going to say out of 20 people, how many ways are there to pick 3 of them where that order is important? And so using our formula here, this is going to be 20 factorial over n minus r, so 20 minus 3 is 17 factorial. 20 factorial is 20 times 19 times 18 times 17 all the way down to 1. 17 factorial is also 17 times 16 times 15 all the way down to 1. So you can see that the 17, 16 all the way down to 1 are going to cancel, and we're just left with 20 times 19 times 18. Now there's something called the multiplication counting principle, or the fundamental counting principle. And what you do is you say, how many choices are there for like a first place finisher? There's 20 ways that somebody could finish first. Once that person finishes first, how many different people could finish for the second medal? That would be 19. And once those 2 people finish, how many ways are there for a third place finisher? 18. So you can use this fundamental counting principle, or you can use this NPR formula for this example. So let's multiply that out and see what that comes out to. Okay, this is coming out to 6,840 different ways to award those 3 medals. Okay, if you want to test yourself on some of these problems, go ahead and pause the video and see if you can do them on your own. But let's dive into number 3. It says, if there are 15 people on your chess team, how many ways can you choose 2 co-captains? So what do you think about that one? Well, what's interesting is, do you think that the order is important? Like if they pick Joe first and Sally second, or Sally first and Joe second, like does the order matter? Well, in this case, because they're co-captains, it's not like the bike race one where like gold, silver, bronze, like you would get a different medal. In this case, they're co-captains, so it doesn't matter. A and B, B and A, they both made it into being co-captains. The order doesn't matter. You want to use combinations. So here we're saying out of 15 chess members, how many ways are there of choosing 2 where the order doesn't matter? So using our formula here, we've got 15 factorial over n minus r, so 15 minus 2 is 13 factorial, 2 factorial. Now again, remember the 2 factorial is dividing out A and B, B and A, those are the same 2 people. So if we simplify this down, you can do this by hand. 15 factorial is 15 times 14 times 13 all the way down to 1. Okay, which you could just write this as 13 factorial. That's going to cancel with this 13 factorial, 13, 12, 11, all the way down to 1. And then 2 factorial is just 2 times 1. 14 divided by 2, we can reduce that to 7. And 15 times 7 is 105. Divided by 1 is just 105. So there's 105 different ways to choose those 2 co-captains out of the 15 chess members. Okay, so for number 4, see if you can do this one. It says, if a school board has 8 women and 4 men, how many ways can a committee be formed with 3 members such that all 3 are men, or all 3 are women, or 2 are women and 1's a man, and at least 1 is a woman? So we've got a multi-part question here. Now when you see the word committee, it's very similar to what we did with the co-captain. So the order, it's not important, right? Because it's not like there's a president, vice president, secretary, treasurer like that. The order is not important when it's a committee. They're just all together. So it says all 3 are men. So we know that there's 4 men, and the order doesn't matter. So we're saying out of 4, how many ways are there of choosing 3? So we would say 4C3. Now on your calculator, there should be a combination button also underneath that probability menu. So I'm going to do that on the calculator. I'm also going to show you how to do it by hand in case you can't use a calculator. This is coming out to 4. So let's just write that here. Now 4C3, using our formula, this is going to be 4 factorial over 4 minus 3, see n minus r, which is 1 factorial, and r factorial, which is 3 factorial. Now 4 factorial is 4 times 3 times 2 times 1 1 times 3 factorial is just 3 factorial, so that's 3 times 2 times 1. And you can see that's how we're getting 4. So let's go to letter B here. All 3 are women. Well, we know there's 8 women, and we want to find out how many ways of choosing 3 women out of those 8 where the order is not important, so it's a combination. So same idea, we're going to do 8 factorial over 8 minus 3 is 5 factorial, 3 factorial. If you simplify that down, let's see what we get. 56. And for letter C, 2 are women and 1's a man. So this one's a little bit different because out of the 8 women, we're saying how many ways are there to choose 2, times out of the 4 men, how many ways are there of choosing 1. Now you'll notice the 8 and the 4 add up to 12, the 12 people on the board, and the 2 and the 1 add up to 3 members on the committee. And we're making use of that fundamental counting principle. We're saying how many ways are there to choose the women, how many ways are there to choose the 1 man, and we're multiplying them together to get the total possible outcomes. So let's see what this comes out to. So 8 combination 2 is 28, and 4 combination 1 is 4. And if we multiply those together, we get 112. So 112 outcomes there. And for the last one, this one's a little bit different. At least 1 is a woman. So that means 1 could be a woman, 2 could be 2 women on the committee, or all 3 women could be on the committee. So when you see at least 1, there's a little bit of a trick here that you can do. You can take the total number of ways of choosing 3 members, okay, out of the 12 members, minus that none are women. Okay, so at least 1 is the total minus none, and that'll give you 1 or 2 or 3 women on the committee. So the total would be 12C3 out of 12 members. How many ways are there to choose a committee of 3 members? Minus none are women. Now, none are women, that was like saying that all 3 of them were men, which there was 4 ways there. And so let's see what 12 combination 3 is. That's 220 minus 4 is 216 ways that there could be at least one woman on this committee. Okay, for number 5, we're going to be dealing with some standard deck of playing cards. And you might be saying, Mario, I'm not a card player. Don't worry, I'm not a card player either. But the thing you want to remember, and you might want to write this down, is what is the breakdown of a standard 52 card deck? Well, of the 52 cards, half are red and half are black. So 26 red, 26 black. Of the red cards, they're divided up into what we call suits. So there's 13 hearts and 13 diamonds. Those are red, okay? Whereas over here, there's 13 spades and 13 clubs. Those are black. So half red, half black, 4 suits. And then underneath each suit, you've got a face card, a king, queen, and jack. They have a face on it, king, queen, jack, and that's in each of the suits. And then there's the numbered cards in each suit. So there's 2 of hearts, 3 of hearts, all the way through 10 of hearts. Same thing with the diamonds, 2 through 10. Those are the numbered cards. And then you've got an ace in each suit. So an ace of hearts, ace of diamonds, ace of spades, ace of clubs. So that's the breakdown. So let's see if we can do some problems here. So it says, how many ways are there of being dealt a 5-card hand out of a standard 52-card deck if all cards are numbered? So what you would do is you'd say, well, how many numbered cards are there? Well, it looks like there's 2 through 10, that's 9. 9, 9, 9. 9 times 4 is 36. So there's 36 cards in the deck that have a number on it. And we want to know how many ways there are being dealt 5 of those cards. Okay, so you're dealt a hand. And so that would be out of 36, how many ways are there of choosing 5 out of that 36? Okay, the numbered cards. Now we're using combinations because the order doesn't matter. When you're dealt those cards, when you're in your hand, you can rearrange them. So it doesn't matter which card you're given first, second, third, because you can rearrange them. So it's the same 5 cards. So let's go ahead and figure out what that is. 36 combination 5. Let's see what that is. It looks like we're about, 376,992 different ways to be dealt all numbered cards. Okay, for letter B, it contains exactly 1 ace. So 5-card hand, okay, and it contains exactly 1 ace. Well, let's see, there's 4 aces. So out of the 4 aces, how many ways are there of being dealt 1 of those 4? times out of the 48 remaining cards that are not aces, see 48 and 4 adds up to 52, how many ways are there of being dealt 4 of those cards out of the 48? So just remember, the first number is like how many you're dealing with in that group, 48 non-aces, and the second number is how many we want out of that 48. Okay, and we're using combination C because the order doesn't matter. So let's go ahead and do this on the calculator. 4C1 is just 4. 48C4 is 194,580, and if we multiply that by 4, okay, we're getting 778,320. So 778,320 different ways of getting a 5-card hand that contains exactly 1 ace. Now, what happens if you want no aces? How many ways are there to be dealt a 5-card hand and there's no aces in that 5-card hand? Well, because we said there's 4 aces, that means there's 48 cards that are not aces, and we want to see how many ways are getting 5 out of that 48. So 48 combination 5. Okay, and that comes out to 1,700,000. Okay, and then for letter D, all our diamonds or all our clubs. Now, in math, let's talk about this for a second. Or means union. It means like combined. It means both. But you don't want to double count. So if you're familiar with Venn diagrams, remember your Venn diagrams. See, here's the diamonds, here's the clubs. Or means both combined together. Now, if there were overlapping, like if there was some diamonds that were clubs and some clubs that were also diamonds, we'd have to double count the ones, we'd have to subtract off the double counted ones. We don't want to double count. But in this case, these are what they call mutually exclusive or non-overlapping. And so what we can do is we can just add the number of diamonds, or the number of ways to get 5 diamonds, the number of ways to get 5 clubs. So how many diamonds are there? There's 13 diamonds. So out of the 13 diamond cards, how many ways are there of choosing 5 of those, where the order doesn't matter? Plus, out of the 13 clubs, how many ways are there of choosing 5 of those? So let's see what that comes out to. This is 1,287 plus 1,287, which is 2,574 ways of being dealt 5 diamonds or 5 clubs. Okay, so for letter E now, what is the probability of being dealt all face cards? Okay, now notice we're dealing with probability. Probability is the number of successful outcomes, or what we want, divided by the total possible outcomes. So being dealt all face cards. So face cards, we can see that there's 12 face cards. So out of 12 face cards, how many ways are there of getting 5 out of that 12, where the order doesn't matter, divided by the total ways of being dealt 5 cards out of the 52 card deck. See, probability, again, it's what you want out of the total. Okay, so in this case, let's see what this comes out to. So 12 combination 5 is 792 ways of being dealt all face cards, and 52 combination 5 is a big number, 259,8960. And you might be able to reduce this down. Here, I'll see if it reduces down a little bit. Let's see, does that reduce? My calculator's not reducing it, but you could reduce it because see how they're both even. You can divide by 2. You can also write it as a decimal approximation. You could even convert it to a percent, but that's really the percent chance. Probability is more like a fraction or a decimal, not a percent. Okay, and then the last one, letter F, what is the probability of being dealt at least 1 face card? So at least. Now again, we're dealing with probability, and we did a similar problem where we said at least 1 woman, remember, in that committee? But with probability, the total is 100%, right? That's everything that could happen. And 100% written just as a number is the number 1. 1 is like 100%. So 1 minus, okay, no face cards. So we're going to do the probability that you get no face cards. And let's see, so no face cards would be, there's 12 face cards, which means that there's 52 minus 12, 40 non-face cards. So that would be 40C5. So out of 40 non-face cards, how many ways are there of choosing 5, divided by how many ways are there of getting 5 face cards out of the 52 standard deck here. And we're going to take that away from 1. So let's see what that comes out to. So 40C5, okay, divided by 52C5. Okay, so this is basically, I'm going to round a little bit. So this comes out to about 0.25. So 1 minus 0.25 is going to be 0.75. So it's about a 75% chance, but the probability is 0.75 or 3/4 approximately, and you got it. Okay, let's take a look at number 6 now. It says, how many diagonals can be drawn in a decagon? So remember, a decagon, it's a polygon with 10 sides. And what exactly is a diagonal? Well, let's do a simpler example. And this is a good technique sometimes. If you ever have a difficult problem, try to do a simpler one and then kind of extrapolate out, and you can solve more challenging ones that way. A diagonal, it connects two non-consecutive vertices. The vertices are the points here on our polygon. So for example, this would not be a diagonal, but this would be a diagonal. This would be a diagonal. This would not be a diagonal. So what's interesting here is you can see you're connecting up 2 points in the polygon, right? And there's, in this case, there's 5 points total. And there's a similar problem that I think I've done before in another video where it's like you're at a party and it's like, how many different ways can, you know, everyone shake hands with every other person, right? So when you're shaking hands, like there's 2 people are involved in that handshake, right? And the order doesn't matter. If A shakes person B's hand or B shakes person A's hand, right? That's the same one handshake. You don't want to double count it. So you're going to want to use combinations because the order doesn't matter. This vertice and this vertice, or this one and this one, the order doesn't matter, but you're pairing up 2 vertices out of the, okay, in this case it's a decagon, so 10. So we're saying out of 10 vertices, how many ways are there to choose 2 to make a line segment between the 2 of them? That's a diagonal. But what's interesting about this is we don't want to count the sides of the polygon because those are not diagonal. So this is a segment, but we want to subtract that off. So in a decagon, there's 10 sides. We're going to subtract off the 10 sides. So let's see what that comes out to. So 10C2 is 45, minus 10 would be 35 diagonals. Now you could try to draw them, but again, that takes a little bit more time. So that's why start with a simple example and then you can apply that to a more challenging problem. Let's look at number 7 now. It says, how many 4-digit numbers are less than 7,000 with no zeros and no ones? Okay, that's an interesting question. So a 4-digit number, let's diagram this out. 1, 2, 3, 4 digits, right? And you want it to be less than 7,000. So less than 7,000 means that this has to be, well, it can't be 0, because if the first digit was 0, then it's only a 3-digit number, right? Can't be 0. Can't be 8 or 9, because then that would be like 8,000, 9,000. Can't even be 7, because we want it to be less than 7,000. So basically that leaves us with 1, 2, 3, 4, 5, or 6. So there's basically 6 choices for this number, but we don't want any zeros and ones, so 1 is out. So that means there's only 5 possibilities for this first digit. Okay, times how many possibilities are there for the second digit? Well, normally there would be 10 possibilities, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 0 through 9 is 10 digits, but we don't want any zeros and we don't want any ones, so 10 minus 2 would be 8. 8 possibilities for the third digit and 8 possibilities for the fourth digit. And if we multiply those together using that fundamental counting principle or that multiplication counting principle, what does that come out to? Let's see. 2,560 numbers are less than 7,000 with no zeros and no ones. So a lot faster than having to actually try to write them down and count all the possibilities. Okay, let's try number 8 now. So it says, how many different salads can be made at a salad bar with 20 different items? Okay, this is an interesting question. So it's just asking how many different, you walk up to the salad bar, you say how many different salads are possible? Well, it doesn't say like you're making a salad with 5 ingredients or 7 ingredients or 3 ingredients. It just says how many different salads can be made. So one way to think about it is it's kind of like a yes or no question. You walk up to the olives, yes or no, right? So basically there's 2 choices. Then you go to the next item, you say, do I want tomatoes, yes or no? Okay, and so basically because there's 20 items and there's 2 choices for each item, it's going to be 2 times 2 times 2 times 2 times 20 times. That's 2 to the 20th power. Now, what happens if you said, no, I don't want tomatoes, no, I don't want lettuce, no, I don't want this. Okay, you say no to everything. Well, then you really wouldn't have a salad at all. So that particular outcome, we're going to say that's no salad. We're going to subtract that 1 off, okay? So we could argue that that's technically not a salad at all. So let's see what this comes out to. So 2 to the 20th, okay, minus 1. So this is 1048575. So about 1 million different salads that you could create. Now, again, you know, sometimes I know students struggle with this permutations, combinations, probability, but if you can understand these basic problems that we're going through, you can apply them to other problems. Like say, for example, it was like a true and false test. How many ways could you answer this true and false test? You wouldn't subtract 1, but you would say, oh, there's 20 questions. I could pick true or false for the first question, true or false for the second question. That's 2 times 2 times 2, 2 to the 20th. So I hope this is encouraging to you to try to apply this to other problems. So for number 9, it says in a warehouse containing 12 items where 4 are defective, like broken, right? Okay, they're bad. What is the probability that you receive a shipment of 5 items where 2 are defective or bad? So if there's 12 items total, that means there's 8 good and 4 bad, right? And you're receiving a shipment, okay, of 5 items, and it wants to know what is the probability. Okay, remember that's the number of successes over the total possible. And what we're looking for is that 2 are defective. Okay, so let's think about it. So 2 are defective. So out of the 4 defective items at this warehouse, how many ways are there to get 2? Now we're using combinations because it doesn't matter the order. We're assuming these are all the same kind of widget, whatever that is, okay? And then out of the 8 good ones, how many ways are there to receive 3 of the good ones out of the 8 good ones? That's going to give us the total number of successes. When I say success, it's like what you're looking for, what you want, divided by the total possible ways of receiving 5 items from this warehouse that has 12 of these items. Okay, so this is the total possible. So let's see what that comes out to. So we have 4, okay, do this on the calculator. Okay, so this is coming out to 336 divided by 792, which is about 0.42. So it's about a 42% chance that you would receive 2 defective and 3 good. For number 10, we have if a person's free throw percentage is 70%. What is the probability of getting exactly 4 out of 5 free throws? So the percentage of scoring is 70%, that's a 0.70. And what we're going to do is let's talk about this binomial probability. So binomial means like bi is 2. So there's 2 possibilities. Either you make the free throw or you miss the free throw. So it's like win or lose, succeed or fail. There's only 2 options, right? And so the probability, okay, when it's a binomial like this, you take the number of trials, okay, and the number of successes out of that number of trials, the probability of success, the number of those successes, 1 minus the probability of success, which gives us our probability of failure, and the number of those failures. So the way we would set this one up is we'd say there's 5 shots that you're taking, that's the 5 trials, and we're looking to get exactly 4 free throws, 4 successes. The probability of making the free throw is 70% or 0.70. We want 4 of those, and the probability of missing is 30%, and we want 1 of those. So let's see what that comes out to. 5C4, okay, times 0.7 to the 4th times 0.3 to the 1st. Okay, so this is coming out to 0.3, approximately 36%, or we just say as a probability approximately 0.36. So that's binomial probability when there's only 2 possible outcomes. Okay, now for number 11, I mean success or failure, right? Win or lose. For number 11, what is the probability of picking a face card or a black card out of a deck of cards? Now here we're talking about about probability, and we talked about the breakdown of face cards, or not face cards, but a deck of cards earlier. Remember, when it's probability, it's going to be a fraction out of the total. So out of the 52 cards total, we're saying how many ways are there to choose one? Okay, but we're saying that it's a face card or a black card. Now there's 12 face cards. We say how many ways are there to choose one face card, plus how many black cards are there? There's 26 black cards, because half are black, half are red. Choose one of those. But you see there's an overlap here. Some of the face cards are black, which means that we're going to have to subtract off the ones that we're double counting, we counted in this group and this group. So that's going to be minus the 6 clubs and spades face cards. Choose one. Okay, so let's see what this comes out to. So this would be, let's see, this is 12 choose 1, which is 12. 26 choose 1 is 26, so that's 38. Minus 6 choose 1 is 6, so that's 32 over 52, which is, let's see if we reduce that down, 4 goes in here 8 times and 4 goes in here 13 times. So it'd be an 8 out of 13 probability, which we can get that as a decimal. It's approximately 0.62. Okay, before we do these last 4 word problems, I wanted to let you know about an Algebra 1 and an Algebra 2 video course that I have for sale. You can check those out down in the description. The Algebra 2 is also suitable for like a college algebra class, so check out those videos where I take you step by step through a typical Algebra 1 or Algebra 2 curriculum. And if you'd just like to support the videos that I'm putting up here on my Mario's Math Tutoring YouTube channel, you like the way I explain things, and you want to help me to keep this going, consider supporting the channel as a channel member. So you can join the channel for a few dollars a month, and I really appreciate that. Let's dive into the last few examples. So for number 12, it says a bag contains 3 red marbles, 4 blue marbles, and 5 yellow marbles. What is the probability of choosing 2 yellow marbles without replacement? So this is important, without replacement. And there's a couple different ways to do this problem. One way to do it, remember how we said probability is what you want out of the total? In this case, we want 2 yellow marbles. So when we reach into this bag, there's 5 yellow, right? And there's 12 total marbles. So the probability of getting a yellow would be 5 chances of success out of 12 possible marbles that you could pick. Once you pick that first yellow marble, when you go to reach for the second yellow marble, there's only going to be 4 chances of success out of 11, because there's 1 less marble in the bag total. So when we multiply these together, you can see we're going to get 20 over 132, which we could reduce this down. Let's see, what does that reduce down to? 5/33. Okay. The other way to do it is use the combinations. You could say out of 5 yellow, how many ways are there to choose 2? And the total possible way of choosing 2 marbles out of 12, you're going to get the same answer, 5 out of 33. So for number 13, let's look at this one. A couple plans to have 5 children, assuming that boys and girls are equally likely. Find the probability that the couple will have at least 1 girl. So we've seen this a lot in this particular video, at least, right? So at least when it comes out to probability, 100% is the total, which is like the number 1, minus the probability that they have no girls. Okay, so 1 minus the probability of no girls means that it's 1 or more. So 1, 2, 3, 4, or all 5. Now, no girls is another way of saying all boys, right? And what's the probability the first one's a boy? It's 1 chance out of 2. What's the probability that the second one's a boy? 1 out of 2, 1 out of 2, 1 out of 2, 1 half, 1 half, 1 half. So that's really 1 half to the 5th power, okay? And we want 1 minus that. So 1 half to the 5th is 1 over 32. 1 is like 32 over 32, minus 1 would be 31 over 32. So that would be your probability of having at least 1 girl. Okay, before we do these last 2 problems, I'll indicate at the end of this video another video that you can click on if you want more practice and more problems to kind of work on. A video that I did similar to this, different problems obviously for more practice. But let's do these last 2 problems. It says you forget the order of the 5-number combination to your safe. If you remember the middle number, what is the probability that you guess the correct order of the remaining digits on the first attempt? Okay, that's interesting. So what do you think for that one? Well, let's kind of diagram this out. So you've got 1, 2, 3, 4, 5 numbers. Now, you know all 5 of the numbers, okay? It's just that you forgot the order of those 5 numbers. But you do remember what the middle number is. So you know what this guy is right here. So let's kind of X that one off. So really, of these 4 digits that you have in your head, you just have to remember what order to put them in, right? So how many different ways could you order these 4 remaining numbers? Okay, now the order is important, right? So we could do this as a 4 factorial. See, that's the number of ways of ordering 4 items. We could also do 4p4. 4p4 is the same thing as 4 factorial. And the reason that is because when you do 4 minus 4, that's 0 factorial, and 0 factorial is 1, which is just going to give you the numerator n factorial or 4 factorial. Or you can use the fundamental counting principle. You can say there's 4 choices for which one I try for the first number, then 3 for that next number, 2 for this one, and then 1 for this one. So that comes out to 4 times 3 times 2 times 1, which is 24. But only one of those is correct, right? So the probability, when you think of probability, it's the number of successful outcomes over the total possible. So this is going to be 1 over 4 factorial, which is 24. So a 1/24th chance it's going to work before the alarm goes off, right? Okay, so number 15, a math professor assigns 30 probability problems from the textbook for an upcoming test, which will have 15 of these problems on it. I should have written these exact problems on it. If you only know how to solve 20 of them, okay, 20 of the 30, what is the probability that you get all the 15 problems correct on this test? So what do you think about that one? So it's definitely a probability problem. So we want to think about this as number of successes over the total possible. And you know 20 of these problems, right? So if your teacher, by some crazy chance, they give you 15 of those problems from the book, out of the 20 that you know, how many ways could that happen, right? Again, the order doesn't matter. They're going to be on the same test. Doesn't matter what order they're in. So that's why we're using combinations. But the total ways that a math professor could choose 15 problems out of 30, how many ways could that occur? So these are the number of successes over the total possible. Let's do this on the calculator. Let's see what we got here. So 20 combination 15. Okay, so this is like 15,504 ways. And 30 combination 15 is like a big number. And if we divide those, okay, we're getting basically 0.0001. Okay, so it's a very slim chance that you're going to get them all right. You might get, some of them right, but the chances that they pick exactly the ones that you studied and knew, this would be how you do that one. So great job if you're able to follow this video. If you want more examples, go ahead and follow me over to that previous video that I did talking about permutations, combinations, and probability. I'll see you over in that video.